All right, so today, like I mentioned earlier, we're going to be doing mostly review. Now, if you are just dropped into Algebra 1 and you're just joining the Excel Center for the first time, this may not be as recent of a review for you, but hopefully at some point, if you were placed in this class, you've probably heard this at least once before. So we're going to cover kind of a hodgepodge of things here, starting with the differences and similarities between expressions versus equations. And each of them by themselves are fairly simple concepts, but what typically happens is that they get confused for one another. So it's very common, I see students trying to do something with an expression that you would typically do with an equation. So being able to identify what you have before starting into the work is significant. So first thing we're going to do here, let's make some comparisons. What do they have in common? What do you see? What do they have? You can be specific or general, whatever you think. They have variable? Yep. So just a quick refresher, if you have a letter in the mix with other numbers and operations, that is a variable. It's representing a number that you do not yet know. What else do you see? Yes, I think. They both have a -7. Thanks, Makai. Yep. In fact, if you look at the numbers themselves, they have exactly the same pieces in the sense that we have a 4x, a +3, and a -7. So let's jot that down. So I'm going to be a little bit more general here. So this expression has numbers, a variable, and arithmetic operations. Arithmetic, maybe you've heard that word before, maybe not, is just your addition, subtraction, multiplication, and division, arithmetic. The four basic functions, operations that you typically start off learning. So it has numbers, a variable, and arithmetic operations. And we said that that was something that they both had. So I'm going to come over here. I'm going to write the same thing. So they both have those. Very, very, very similar. But hopefully there's one very, very immediate difference that we can pick out. Go ahead, Jay. The equation has an equal sign, therefore you're suggesting the expression does not. Absolutely. So I'm actually going to start here on the left-hand side. I'm going to write that it does not have an equal sign. I'm actually going to underline that as well, because that key difference tells me a whole lot more. It actually tells me that this can only be simplified not solved. So an expression has all the same pieces except for that equal sign. And without an equal sign, you cannot solve it. That doesn't mean you can't do other things to it. That word simplify, we'll talk more about that here in just a moment. But you cannot solve it, which means that unknown piece, that variable, that value that's missing, we're not going to be able to figure out what it is. Because an expression is just a relationship, but it's not a comparison to where we can actually evaluate to find that missing piece. Now, As Jay pointed out very specifically, the equation has an equal sign. So we'll say does have an equal sign. And for us, that means that the variable can be solved. Meaning that through a couple maneuvers, we can figure out exactly what that missing value is for that variable. The only value that would make this equation true, meaning that the left side does in fact end up equaling the right side. If you ever need me to zoom back in, don't hesitate to let me know. So if I was to oversimplify this, expressions can only be simplified, not solved. Equations can be solved because of the equal sign that they have. So very important difference there, because that changes how we approach the problem, and that also changes how far we can take some of these examples. Now, we're going to stick with expressions for a little bit longer here for just a moment before we switch gears to equations, because we are going to try to juggle both today. And for expressions, one of the big things that come into mind is the order of operations. So hopefully you've heard of this before. Maybe you've referred to it as PEMDAS. Please excuse my dear Aunt Sally. Basically, it's just an acronym that helps you remember what things you need to address and in which order. If you're not being careful and you do one of these out of order, it actually changes the outcome. So we're going to start over here and jot down our order of operations. So does anyone know what P stands for? Parentheses. Now, sometimes I go slightly off topic, but sometimes it actually pays off a little bit. In some other countries, I think particularly in Europe, when they discuss the order of operations, they actually use the letter G instead of the letter P, because instead of saying parentheses, they actually say grouping symbols. And the reason for that, the reason why I actually like that a little bit better myself, is because parentheses, if you just are considering parentheses, you're limiting yourself and excluding a long list of other types of grouping symbols that must be addressed first before any of your other operations. So parentheses are the ones that we're probably most familiar with. Those are the little curved pieces. But in this same category, we would also include brackets, which are the squared ones, braces, which are the ones that everyone groans about trying to write because they're a little squiggly. And there's actually several more. There's absolute value bars. There's one that we'll get to towards the end of this course called radicals. But all of these symbols kind of have the same purpose in the sense that they group things that are within them. So parentheses, yes, that's the one we all learned for order of operations. But it's really all grouping symbols in math that need to be addressed first, because those grouping symbols are saying, hey, these pieces all have something that they need to do together before you worry about anything else outside of them. We'll see some more examples here today. What about E? Exponents. Now, maybe you've spent some time with exponents, maybe not. Odds are, if you're dealing with exponents, it's probably something like a big number raised to just a little number floating just to the right of it. In which case that tells you how many times to multiply the bigger number together. I'm not going to go too much into detail with it. yet, because in unit 4, we actually spend an entire day talking about nothing but exponents. There's actually a whole lot more going on with them than what we typically just use them for. So they'll come up a little bit today, but after today, they won't come up again until unit 4. But they do come second in our order of operations. What about the M? Multiplication. Not really a whole lot to say there. Multiplication is a number times another number. What about the D? Division. Again, same thing. Hopefully we've done a lot of division up until this point. But here's where some of the confusion comes in. And some of you may already have learned this before, which is great. But multiplication doesn't always come before division. And the reason for that is multiplication and division technically are on the same level. Now, this is actually where a lot of those, I don't want to say they're not memes, but those posts online that say 99% of people can't solve this simple math problem. It's usually an order of operations problem, and it's usually because of this little sneaky bit here that says that multiplication and division actually occur at the same level. And if you have both, you're actually supposed to solve them from left to right. Which means that there will actually be occurrences where you will perform a division before a multiplication. And that's the trick. It's always amazing how many people get so heated in the comment section because they're just bound and determined to say, no, you always do multiplication before division. That's what order of operations says. No, actually multiplication and division are two sides of the same coin. What about the A and the S? Addition and subtraction. And interestingly enough, they actually follow the same rule. Addition and subtraction are actually two sides of the same coin as well, which means, hypothetically, there will be occurrences where you will perform a subtraction before you'll do an addition. And that again is assuming that the subtraction is left of your addition. Now, some of you may have heard that in Math B because I think we've been trying to trickle that back a little bit more just so you can hear that a couple more times. But if you're just now joining us here at the Excel Center, this may be news to you because for the longest time, I did this incorrectly myself. Any questions so far? Order of operations, PEMDAS. If not now, hopefully, if you do have questions, you can ask me later. What I want to do real quick is use our order of operations, or at least most of them, to evaluate this expression. Now, the reason why it says evaluate, hopefully, you notice it has no what in this mix. Sorry?
Equal sign.
There's no equal sign. So we can't actually solve it in the sense that we're solving for a, what else is missing?
Variable.
Variable. So there's not actually anything to solve for. In reality, this is just a bunch of operations being performed. When we're done with this, we should just have a value, which is why it's called evaluate. When you're done, you have a value. What we want to be careful of, though, is that we're not getting things mixed up. So I always recommend if you aren't using it, bring it along. That's actually something that I talk about quite a lot in here, is don't be lazy, write things down. Your work that you write down should be neat to the point that if you were to follow your steps in reverse, you can trace where every piece came from, where every piece went. Sounds like a lot of extra work now, but I promise you, if you pay extra attention to those details, if you take the time to write neatly, it will pay off. So the reason why I say that is because sometimes, so don't write this down. Sometimes I'll see students say, okay, well, -6 minus a -3 is a -3. And then -4 times -5 is 20. And then I try to figure out what to do with this 6. And the next thing you know, you've got numbers floating all over the place. I don't want that. Because if I then said, okay, well, where did some of these values come from? Depending on how scattered your work has become, it's going to be really hard to retrace your steps. So organization is key. I'm going to harp on that a lot. You're going to get real tired of me by the end, but if you listen to me at least a little bit, you're going to develop some really good habits that are going to carry you pretty far. So right off the bat, what should be drawing our attention first? Parentheses. And actually, we also have those brackets, which kind of behave the same way as parentheses. So we've kind of got two layers of parentheses, so to say. Now, if I look inside the first brackets, it looks like these parentheses, are they really doing that much? No, if you may actually notice that they're doing something that a lot of people do. They're saying, hey, these values inside are negative. Don't lose this negative sign. So there's not going to be much we can do there. And then in the second bracket, we have, again, another set of parentheses being used for that same purpose. So here the parentheses themselves are kind of a visual aid. The parentheses themselves, we can't do much, but we can still focus inside those brackets. So long story short, what's something that I'm not even going to touch here at the beginning? That 3 out in front, that 3 in that division. I'm not even close to it. I've got to work inside these brackets until they're cleaned up significantly. So if I'm not using it, I'm bringing it down along for the ride. So then I get to this first set of parentheses, or excuse me, brackets. And inside I have -6 minus a -3. Now, hopefully, depending on where you're coming from, some of you might be able to answer this to me. It's a positive. Subtracting a negative, a double negative, whether it's in English or in math, actually means a positive. So if I was to rewrite this, this technically is -6 plus 3. I'll come back to that in just a moment. So that's cleaning up a little bit the first set of brackets. Let's see if we can do any cleaning in the second set of brackets. In there, I see 6 minus 4 times a -5. The parentheses, like I said earlier, is really just helping us remember that this 5 is in fact negative. So the question then technically is, am I going to do this multiplication first, or am I going to do the subtraction?
Multiplication.
Multiplication. Subtraction never comes before multiplication. So what I'm actually multiplying here, I'm actually going to use that minus sign technically, and I'm going to take that -4 times a -5 to get what?
Positive 20.
A positive 20. And that's my first step. I've changed only a couple of things, but what hopefully you should be able to do then is say, you know, where'd this 3 come from? Oh, it was already there. -6 was already there. Where'd the positive 3 come from? Oh, that was subtracting a negative. 6 was already there. Where'd the 20 come from? Oh, that was the -4 times the -5. Showing these steps help, I promise you. Then it sets us up really nicely to move on to our second step. Am I ready to touch that 3 and that division sign yet? No. I assume you said negative in the sense that that's a no. So we still have some work that can be done inside these brackets, which behave a lot like parentheses. So in our first set here, what is -6 plus 3? That's all that's left in there. A -3. And then in the second set of brackets, what's 6 plus 20? 26. So already it's getting compressed down very quickly. Now, I will point out that we do very clearly see the division here, but I do have two sets of brackets or parentheses or grouping symbols side by side. What operation does that actually signify? Multiplication. And you're going to see that a lot. You know, anytime a number is next to a variable or a parenthesis right up against a parenthesis or a number is right up against a parenthesis, those all signify multiplication. Now, if you're a little worried you're going to forget that, there's no rule saying you can't put a little multiplication dot between them, just as a visual cue. But that's going to help us out a lot. So our second step is complete. We're getting a whole lot closer. So I still have these brackets. That's okay. They're kind of just telling us about that multiplication. So really, my question is, will I do the division first or the multiplication? Sorry? But in PEMDAS, M always comes before D. When multiplication is paired with, you're right, I'm just pushing a little bit further. When it's paired with division, all we have left here now is multiplication and division. And when that happens, you always go left to right. And that's good because if I went with multiplication first, I would have gotten a really weird fraction. But doing the division first, what is 3 divided by -3? A -1. Bring down my 26 that I haven't used yet. Last but not least is that multiplication. What's -1 times 26? Heard it mumbled. -26. It's done. So again, the idea here is we've reached the conclusion, we've reached the end of the story, but if I wanted to, I should be able to trace each step back to its previous step before it. So -26, well, that was -1 times 26. Where'd the 26 come from? Oh, it was already there. So where'd the -1 come from? Oh, that was 3 divided by -3, and so on and so forth, all the way back to the beginning. So there's an analogy I like to use. I use it every term, and I use it multiple times because it seems like a very down-to-earth example. And that is, would you be considered a good mechanic if you could just take the car apart? Why not? You need to know how to put it back together again. To fully understand something, to be good at something, you need to know it both forwards and backwards. So every once in a while, if you take a moment to think, if I were to think about this in reverse, can I retrace my steps? Can I recreate what I started with? You know, and you think mechanics, well, one, they make excellent money when they're good at what they do, but they follow that same principle. Math is no different. Math, you just need to be able to take it apart and put it back together again. All right. Any questions on simplifying an expression, or it's technically evaluating the expression because it had no variables, or order of operations in general? Again, if you're not confident to ask yet, hopefully you're making a note of it somewhere on your notes to ask later. I'm okay with that as well. So there's one more thing I want to talk about before we transition to the backside, which is all things equations. And that is a specific type of expression called an algebraic expression. So an algebraic expression, I'm going to highlight this here, contains variables. Still an expression, order of operations still apply, but because of that variable, we're now limited in just how far we can take it. Because before, we had no variables, so we could take it all the way down to just one final number. But if you have a variable, you have a number that you don't know yet. And because it's not an equation, you're not going to know it. So there's some reminders here that I want to give you. All we can really do is combine all the like terms. There's a reminder that says that like terms must have the same variable combination. So we're going to start off easy, and then we're going to work our way up. Do we have any like terms here? Yes, Jay. 6x and x. Did you say 1x? I like that you said that because a lot of times, and you're going to see this often, ones like to hide everywhere. Now, if you're a very visual person like I am, sometimes it helps to see the one, in which case I would recommend draw it in there. But Jay, you said the 6x and the 1x are like terms, which means when combined, what are we going to get? A 7x. What happens to that -8? Just falls right down next to it. Can I then combine these to get something like -1x?
No.
Why not?
Because they're not like terms.
Not like terms. Oops. One has a variable, one does not. I try to combine them and get something new. That would be like saying I have 7 apples. I'm going to take away 8 oranges. I'm going to get -1 coconuts. Makes no sense. You can't combine things that aren't the same in math. So this is it. This is as far as I can take it. All I could do here is combine like terms as far as I possibly could. And I end up still with an expression, but one that has at least fewer terms. What about this next one? What's jumping out at you, hopefully, at the very beginning? Well, there's a negative. I heard someone else say something else. Parentheses. Hopefully, we reach a point where order of operations has it so ingrained that anytime you see parentheses, we should stop and ask ourselves, is there something I can do with those? Now, this one's a little bit unique because if you look inside the parentheses, I have a 2a and a -3. Are those like terms? No, so I can't combine them. However, Toby pointed out there is a negative out in front, and technically that negative has to belong to some number. There's a 1 hiding there. So technically, there is a -1 sitting outside of these parentheses. And as I mentioned earlier, anytime you have something butted right up against another set of parentheses, what operation is that representing? Multiplication. But Toby, you actually answered my second question ahead of time. It's a very special form of multiplication here called distribution. So you may have learned previously that there's a neat little property called the distributive property. Which for our purposes, I'm going to call it fancy multiplication. It's fancy because it's not just multiplying with one thing, it's multiplying with everything inside that set of parentheses. So what's -1 times 2a? -2a. And what's -1 times -3? +3. Cool. That took care of the parentheses that were catching my eye. Now can I combine these?
No.
No. Why not? They're still not like terms. One has a variable a, the other has no variable whatsoever. This is as far as I can take this one. I'm going to kick it up one more notch. 3w minus 4, and then in parentheses, w plus 1. What should hopefully catch your eye first? Parentheses. They're going to be in the mix a lot through this course. So in this case, first thing I'm going to do is I'm going to look inside the parentheses. Can I combine the pieces inside?
We can.
Inside,
Yes.
w and 1. So unfortunately, the w is a variable. And if you want to see the one that's in front of it, you can. But what does the 1 not have? It doesn't have a w as well. So unfortunately, since they don't both have the same variable, I can't combine them as like terms. But the parentheses tell another story, and that has to do with the number right out in front of it, which in this case is a -4. If you ever are curious about what the sign is of a value, always look immediately to its left. That sign stays with that value when you're using it. So in this case, we're going to take the -4 and do what with it? Just multiply it or distribute it. Jay, was that what you're going to say? Yeah, if you want to see that one, and it's kind of cramped, but if you need to see that one there, by all means, write it in there. I will do it, I'd say half the time. Other times I leave it just to kind of get you comfortable with the fact that they still represent the same thing. But going back to that -4, we can distribute it. What's -4 times 1W? -4W. What's -4 times +1? Someone may have said that. I just probably -4. Am I missing anything? 3W. Do I need to distribute to that as well? Just bring it down. If it's not next to the parenthesis or in the parentheses, I'm not ready for it yet. But I did just knock out the parentheses, which is good. Is there anything more I can do to this expression to further simplify it?
Yes.
What do we got?
Subtract 3W.
So 3W and -4W, because they are like terms. What is 3W take away 4W? -1W. Can I combine the -4 with it as well? No. So bring it down. This is as far as it can take us. So what sometimes throws people off a little bit here is that these don't quite feel like answers because it still seems kind of a mystery. I still don't know what W is or what A is. I don't know anything more about the variable. All I've managed to do is, get rid of the parentheses and combine things that have something in common. Typically, that's a variable. But that doesn't mean that it's any less of the answer that we're looking for. In fact, being able to simplify expressions will later on help us solve bigger and messier equations in later units. We'll always go back to, can I get rid of parentheses? Can I combine like terms? That is not going to go away. That'll always be something that hopefully will sit in the back of our mind, even as the problems seem more complicated. So, simplifying expressions without variables, technically it's called evaluation. You'll get just a value at the end. Throw in some variables, you can still simplify it, but you're not going to be able to take it all the way to what feels like an answer. You're just going to be able to get it as compact as possible. Are there any questions about expressions? And those are the things that don't have equal signs, cannot be solved, but they can be simplified. Okay. So we'll switch gears then. Let's look at the other side of the story, which is the equations. These do have equal signs, which mean I can, in fact, solve them. Find a final solution to finally know what that variable, that mystery number is. Now, what I'm going to do, because one-step equations really aren't that exciting because they literally, as they suggest, take one step. But what I'm going to do right now is something that you're going to see me carry over tomorrow when we do multi-step equations. And this is a visual aid I like to use to help keep your work as organized and as neat as possible. Now, I know some people write very quick and very haphazardly. That's okay. My best friend working on his doctorate has some of the worst handwriting I've ever seen. What I'm going to encourage from you, though, is try to slow down and try to write as neatly as you can.
Hi, sorry to bother you, interrupt. Apparently I got fired over the weekend.
So solving one-step equations, two-step equations, it could be 100 steps. I'm going to try to instill some habits now early on while we're crawling before tomorrow we start walking, and then in later units we're going to run through these problems because we've established these habits from the beginning. Now, when we say solve, we've got a goal. That goal, get the variable alone on one side of the equation. That's it. Variable needs to be by itself. Now, because of that equal sign, we have technically a left side of our equation and our right side of our equation. So it's really important that we know where our variable is, and then we ask ourselves, is there anything else on that side that I need to move? If there is something we need to move, all we need to do is the exact opposite of what is already being done. Opposites cancel each other out in math. So just a quick test here. What's opposite of addition? What's opposite of division? What's opposite of subtraction? What's opposite of multiplication? And there's actually more operations we'll introduce later on in Algebra 1 and then even further in Algebra 2. But every operation has an opposite. It's called the inverse operation. That's going to be very handy here. But let me show you what I've kind of been hyping up here, and it's going to seem way less exciting than what it sounded like before. But anytime you're working on an equation, and if you're still struggling to keep your work nice and neat, try this trick. Find your equal sign. Now, if you're using a pencil, maybe it's like this very lightly, but create a wall. That way, very visibly, I can see the left side of the equation and all that's on it, and the right side of the equation and everything that's on it. The one thing that I don't want to ever move is that equal sign. It seems silly. It doesn't seem like a big thing. But as the steps grow, and we're doing 3, 4, 5 steps, we can always go back to our comfort zone of where that equal sign is. We can then keep track of what's on the left, what's on the right, and if something moves, why. So in this case, we're trying to get the variable by itself. Which side of the equation is our variable on? It's on the left. Is it by itself? What else is on the left? The negative 19. I want the negative 19 to move. How would I move it? Ooh.
Divide.
I heard add and I heard divide, and I'm glad I heard both, because sometimes the first thing we see is that negative sign. But the question that I would then ask, well, actually, Jay, go ahead and give me your answer as well.
Unless that makes me think of when you like do a horizontal line with 1938. And then I cancel out the 19 and just do
Okay, and you kind of alluded to it, so you kind of technically already answered what I'm about to ask you. What does that little horizontal line you're describing represent? Division, which I heard someone who said division earlier. Okay, so I'm hearing a couple votes for division. Addition isn't unusual to hear because that is, again, something that we can very visibly see. What we don't immediately see is the fact that when you have a number next to a variable, that is representing multiplication. So that is negative 19 times m. I'm going to do the opposite. Instead of multiplying by negative 19, I'm going to divide by negative 19. And Jay used a horizontal line. He described it very clearly for us, which kind of makes us think fractions. But maybe no one's ever told you this before, but fractions are just division in disguise. Anytime you have a fraction, you take the top number divided by the bottom number, you divide it. Now, what's nice, though, is here on the left, negative 19 divided by negative 19 technically becomes a positive 1. But what do ones like to do? They like to hide, which works out in this situation because I'm going to hide it instead of showing it next to the m. And then on the right, I didn't actually say this, but it's very important that whatever you do on the left, you do on the right, because that keeps our equations balanced. Jay just jumped right to it, so I forgot to say something about it. But what is negative 38 divided by negative 19? Positive 2. The variable's by itself. This is solved. That's it. The only way this equation would be true is if the variable m was 2. Okay. I'll prep the second one here. I'm going to give myself a little bit more space. Technically, this is a one-step equation. However, I'm going to make a personal recommendation. Anytime there's a double sign, I highly recommend taking one additional step to clean it up before you go into solving. And in this case, minus a negative is the same as a positive or addition. So I could rewrite this same equation as negative 3 equals x plus 13. And the reason why I like to do that is because in the moment when you're thinking opposites, you may accidentally try to add a positive 13 because you think, well, that's just opposite of minus a negative. We're only doing opposite of the operation, not the opposite of the sign. So what I have found is if you can take a moment and clear up any minus a negatives or plus a negative or minus a positive or any double signs that may show up, it's going to help make it a little bit more clear as to how you're going to move any pieces you need to move. And in this case, where's my variable? By the equal sign, it's on the right-hand side. Is there anything else on the right-hand side? 13. How would I make that 13 disappear? Subtract it, because 13 minus 13 is 0. But whatever you do on one side of your equation, you got to make sure you do the exact same to the other side. So on the left here, negative 3 take away 13 is going to give me a negative 16. X just falls on down. 13 minus 13 is 0, which is why we don't see it anymore. But here's the thing, and it seems silly, maybe for some. Technically, we've answered this. The variable is by itself. But here's another one of those Josh recommendations that are going to pay off later. To really bring your solution to its completion, it is a good habit to write it where your variable comes first. So again, it seems like an extra step, and with equations, it technically is. But later on, in fact, I think Wednesday, when we introduce what are called inequalities, having this habit where the variable always comes first will pay off even more then. So my final answer for this equation is that x would have to be a negative 16. Last one-step equation here. What side is my variable on? What else is on the left? 6. But it's in a fraction. Now, earlier, though, we said that those fraction bars also behave as division. So I would have to multiply by 6. Now, everyone has their own way of showing multiplication. If you like to use the dot, great. What I found, or at least what's a little bit more compact, I personally like to use parentheses to show multiplication because it allows me to show very big multiplication with a little bit of space. So if I was doing it personally, I would say that I'm multiplying the left-hand side by 6, as well as the right-hand side by 6. because parentheses can also be used to represent multiplication. Now on the left, the 6 being multiplied with the divided 6, simplify to a positive 1, and we like those ones because they hide. On the right, 5 times 6 gives me 30. And that's it. Now, I want to throw out there, because there's always at least one, and it's okay, because it's a habit you develop to overcome, situations like this. Some students would sit there and think, well, I already know 30 divided by 6 was 5, so I'll just write down the answer as 30. That's great. And you certainly can do that pretty easily with one-step and maybe even two-step equations. But if you don't take the time to show how you are moving those numbers, how you are getting them away from the variable, when we get to more complicated problems, doing it in your head just doesn't become practical anymore. So yes, I think probably with a little bit of time, most of you could have found all these answers just from your head. But I want you to overcome that reaction. I want you to try to show me how you are moving these pieces. I don't think it's too much to ask, because for the most part, you're only moving one thing for these one-step equations. Any questions so far? We're in the home stretch. We're doing pretty well for time too. Well, if we can move one thing, then in theory, we can move two. So we're going to kick it up to the next notch. This is the most we're going to get to today, and that is solving two-step equations. So now, instead of just moving one thing, we're going to move two. The goal, if you notice, is still the exact same. When I say solve, I mean get the variable by itself. Now, because there are two things to move, this poses a new issue as to what do I move first. So my recommendation, typically, the pieces that are furthest from the variable move first. And the way I like to see it is, I like to think of them as layers. I got to peel out the outer layers first until eventually I get all the way down as close to the variable as possible. And whatever is closest is going to be the last thing that I can move. Now, I'm a creature of habit, and I like to try to develop positive habits. So again, I don't want my equal sign to move here. I want to be able to track what's on the left, what's on the right, and if anything moves, I'm also tracking how. But on this one, where's my variable? It's on the left. What else is on the left? A -5 and a +5. Which of those would you move first? The -5. How? Sorry, Jay. One thing that I do, eventually we reach a point where some teachers tell me it's chaos, but shout out the answer, because I usually pick up on everything. We're going to say the same thing, Jay? Yep. So that -5 is further from the variable. That +5 is too close yet. We're not ready to deal with it yet. It's too close to the variable. So to make the -5 disappear, I'm going to use a +5, which is opposite of -5. And a +5 on the right. Oh, wow. On the left, the -5 + 5 is 0, which makes it disappear. I like to see that. So I bring down the +5 in. On the right, 50 + 5 is going to give me 55. But we're not done yet, because the variable is not by itself yet. What still needs to move? The 5. How are you going to move it? Divide. Because it's being multiplied with n right now. We do the opposite. We divide by 5 here. Whatever we do on one side, we do the exact same to the other. So n is going to equal 11. That's the only value n could be in order for that equation to be true from the very beginning. And again, because I'm showing my work and I have that visual aid or keeping my equal sign in line, I can see each step where I added 5 to both sides, or I divided 5 from both sides. And on to the next one. What side is the variable on? It's on the right side. So from the right side, what do you suggest we move first? Well, technically it's a -6, but what would you do? You would add it, because a -6 plus 6 would be 0. Why did you not move the 2 first? Yep, get the furthest piece out of the way first. That 2 is too close. I got to get everything else out of the way first. So on the left here, adding 6 to both sides, -12 plus 6 is going to give me a -6. The x divided by 2 falls down, and the -6 plus 6 is 0, which for our purposes is gone. Now what are we going to move? Yes, Jay. Yeah.
Fractions definitely should be done a lot. We can use two to multiply all of the last one.
Yeah, so at the end, it does look like a fraction, but I want us to reach a point where we recognize that fractions also are just division in disguise. So technically, we can see this as x divided by 2. Therefore, the opposite would be to multiply by 2. But whatever you do to one side, you have to make sure you're doing it to the opposite side. Yeah.
I'm fine for today, but I really bad vision, so.
Yeah, there was an open seat today, but yeah, absolutely. You can grab one of the front seats for sure. So 2 times -6 is going to give me a -12. On the right, the 2 that's being multiplied simplifies with the 2 that's being divided. Oh, my screen froze. There we go. Which simplifies to 1. What's the last thing that I should do just as good practice? Flip it around so the variable comes in front. So x equals a -12. Good. Last one. I've tried to make some that look a little bit scarier than what they actually are. Multiplication first. You're absolutely right. I'm curious though. What made you choose that?
Because there's that horizontal line, means that whole equation is division, so you get rid of the 4.
So because everything's being divided by 4, it really is messing everything else up, isn't it? And you're spot on. And I'm going to take it one step further before we go with that multiplication. If you try to move the -10 first, you're fooled, because that -10 isn't actually a -10 because it is also being divided by 4. So if you wanted to move it, technically you'd have to move it as a -10/4, which who in here loves fractions?
I absolutely hate fractions.
Awesome. Me too. So I avoid them when I can. So by multiplying both sides by that 4, we're that fraction element out of the way as soon as possible. But whatever we do to one side, we have to make sure we do it to the opposite side. On the left, the 4 multiplied with the 4 being divided, simplify to 1, disappear, hide, whatever you want to call it, leaving us with -10 plus a. On the right, -1 times 4 is going to give me a -4. Yes.
So you add 10 to both sides, then you get +6.
So add 10 to both sides because our goal is still to get that variable by itself. So on the left, -10 plus 10 is 0, which disappears. And -4 plus 10 on the right gives me a +6. That's it. So again, nothing probably groundbreaking today. Hopefully most of this, maybe all of it, felt like review. But because of how often we're going to use these skills and how we're going to grow from them, it was important to kind of establish some norms, some regular ways of writing it to where we all kind of follow it together. All right.